Okay, so it's been a long time, and I have no idea if you remember anything or if I remember what I was doing. But okay, let's try and see. In the last couple of lectures, we introduced the concept of category. We spent pretty much one lecture trying to understand the basic ideas of what a category is. There was some objection at some point that I don't get the right, and I like this objection, I don't get the right to say that I understand what category theory studies unless I know how to get from a category to another category, and we haven't seen that yet. So we are already like 2 lectures in category theory, and we don't know what it means to get transported from a category to another category, just like probably like in the first couple of lectures of group theory, you haven't met what it means to, what are the means that get you from a group to another group, and this is, as we know, what are the arrows in groups, in the world of groups? Somebody help me. Thank you. Okay, so like probably you haven't seen homomorphisms in the first lecture, and we haven't seen the ways that get us from a category to another category yet. I hope we will do this today. But just to remind you what's going on, like in a category I have objects and I have arrows, and they are required to satisfy certain laws. Not so many things, pretty much each object needs an identity and it needs to behave as an identity. This is the law. And as soon as I have like a diagram that looks like 2 consecutive arrows, like that, the category is required to give me which of all the possible arrows that I have from here to here is designated as the one that's the composition of G of f in this case. Might say, okay, so like, sorry for this, like this one is the composition of G of f, and you may have like many possible answers here, but, sorry, this is f, and this is G, but the category like will say, okay, it's this one that will be the composition of, if you compose like f and G. And we have seen this, and we have seen various examples of categories. First, some like very basic ones, like the empty category. You cannot get simpler than that. No objects, no arrows, and all the laws are trivially satisfied. Increasing the complexity, we have the one category, just one object, and I cannot stop here, because one might say, okay, I can find the simpler, something between the empty category and the category 1. In simplicity, okay, maybe it has only one object, but then you break the law that every object needs to select one of its possibly many end-though arrows, let's say, and say this is the identity, and this means that if you have an object and no arrows, this is not really a category. You already don't have the data you need, let alone the laws. And similarly, you cannot have an arrow without objects, because every arrow has a source and a target. So like the second simplest category that you can consider would be like something like that. You have an object and the only arrow that you're required to have, which is the identity. And we have studied a bit, I will not complain yet, I will complain about 30 seconds, but like some homework has been done here. So I think we understand pretty much what's like these very simple categories. We discussed a bit what it means to freely generate something, because I thought I could use it, but apparently we will have to come back to it because it's not so well known as I realized. And we have seen also 2 important parts of like 2 important families of categories. Those that come from posets, or prosets maybe, it's better. Like these 2 that are drawn here, where the idea, the role and the responsibility of the arrows are pretty much to say, yes, you can go from here to there, and that's it. Which means that you cannot, in these categories, you don't have any 2 objects you will pick, you will have at most 1 arrow. These are like, we say that home sets, which are these things, which I have been denoting like that, are sub-singletons, where, just remind you, sub-singleton means at most 1 element. So if I look at that, and I have never seen, like if you just stepped in my class right now, and you forget this thing, and maybe like keywords like that, and you just look at this, you may say, okay, this guy is doing order theory, studying pre-orders, and these are like Hasse diagrams, right? Because they are. And so the idea is that, in this sense, a category is a generalization of a proset. In the sense that, now you get to name the reason why this is less than of that, and you may have different reasons why something is less than something. And out of all the possible reasons, there are two things that happen here. Out of all the possible reasons that an object, like if you're in a proset, thanks to reflexivity, you know that you have this little arrow there. But like if you permit more reasons that something can be less than or equal to something, it means like in this case, you may have a bunch of arrows like that. So the equivalent law of reflexivity, which now becomes the identity, is that you need to tell me which of these things is the identity arrow. Okay, you need to have it, but you also need to tell me which one it is. And similarly, if you have like two arrows like that, and you are in a poset or a proset, transitivity guarantees that you have an arrow like that. And this is exactly the reason why you never draw this arrow when you're drawing Hasse diagrams. You say, okay, what about this arrow? Well, there is a path, I can see it, that goes from A to C, which means I don't need to pollute my, waste the resources of our planet with pixels or whatever, to draw these silly arrows here, and for the same reason, I will not draw all these arrows here. Okay, but now that you have possibly more than one ways that you can compare these things, you need to have, the world you're studying, which is a category, needs to tell you, for example, if you compose this with that, which of these two is the composition of them? So like, if A is less than or B for this reason, I'm considering this way that A is less than or B, and B is less than or C for this reason, the composition of these two reasons must give me a very specific reason of why A is less than or equal to C. And this has to happen in an associative way, because as you understand, if I have a fourth object here, I could get into trouble as soon as I have like arrows like that. I meant to change the color, I changed the width here, like, okay, you have like this, maybe you have like two arrows like that, and then you have like arrows like this. Okay, so I hope you understand where I'm going at here, like this choice of the composition of the operation must be associative in the sense that you need to get to pick like a path like that, and you should know in which to which path this corresponds out of all possible paths from A and D. And it should not matter if you say, okay, I will first take a break here and then go on there, or if I'll take a break here and then compose these two. Okay, so this is pretty much summarizing some ideas we have already seen, and I will keep summarizing them, but there's a question already. So. Okay, so the question is, if I don't have any, by stihia you mean objects or arrows? Objects. Okay, so. Okay, so the question is like a more fundamental one. What does it mean to travel, let's say, from an object to another object, right? Because it seems like, if I understand the question of Areti, it seems like in order to be able to get, to have two ways of going from A to B, I must have at least some different objects like that. And now it looks like I have 1, 2, 3 ways, right? That's your question, right? Okay. So first of all, even if I tell you that C and D are distinct objects here, so in fact you have like 4 objects, all these are distinct, you don't really get to tell me that you see 3 ways of going from A to B. You see, if this is the category, you can say I have at most 3 ways. Here's one, here's another one, and here's another one, right? But like if I have drawn all of the category except these little identities here, these little arrows, right? it's still only one way to go from A to B, because this composition here is forced by the fact that I only have one arrow here, is forced to be equal to this arrow. So I don't have three ways here. I have, how many? Like one, right? Which is this arrow, which can be written like that or like that. And just to give you an example, like it could be like, I could be in this category here with divisibility, and I could have like 2 divides, I don't know, help me out here, somebody, okay, divides 4, or maybe divides 6, and 6 divides 12, and then 2 divides 3, but 3 also, okay, bad example, 8 maybe, is that okay? No, that's not okay, definitely, 4, yes, thank you, okay. So, how many ways do I have in this category to go from 2 to 12? Yeah, I only have one way, right? Because in this category, there is only one way to go from A to B, because I just list these facts like check marks. Yep, 2 divides 12. And this way, you can break it like that if you like. In this sense, you say, it's 2 times 3 equals 6, which justifies this arrow, and then 6 times 2 justifies this arrow, and then 2 times, 6 justifies this arrow, and so on and so forth. Okay, so let's see a category where, in fact, you have, it's not a prosetal category, it's not a thin category, which means that home sets are not sub-singletons, and, okay, probably the best example here, I'm not sure which is the best. Sometimes the best is like the simplest you can think of, and let's try to make one, the simplest we can think of, which is be something like that. You have an object. Which object? It doesn't matter. It's panos. Okay, and you have 2 arrows. What are these arrows? It doesn't matter. It's a star and a bullet. It's an A and a B. Okay, and you have to say which of these is the identity. And now you have a way of going like from panos to panos, travel through whatever A means and travel through whatever B means. The bad thing with this very minimal example is that this phase goes like, yeah, I don't really see it. So like consider the category of sets, where objects are sets and arrows are functions. So pick like your favorite set, supposing it's not a very specific set. So I will pick my favorite set, like, okay, it's 0, 1, and okay, maybe any set that has, okay, I'll pick the natural numbers, just to make it more, I don't have the identity function because this is the natural numbers. And the identity function should go from a set to its set, okay? But okay, let's say, okay, I'll make it even bigger. Okay, so consider but now I don't have 2 objects. But anyway, they shouldn't be distinct, the objects. So take this object in itself, and let's see how many arrows I have from here to here. As many as functions as I have from the natural numbers to natural numbers. Does that make sense? Okay. Any other questions? No, okay. So, one very important family of categories is the thin categories that you can see categories as a generalization of prosets. You need to take more things into account because you may have more arrows, and reflexivity corresponds to identity, and transitivity corresponds to composition. I've hinted on this in the first lecture of categories, I think. There is a very important mentality that you need to apply in order to go from the idea of a proset to the idea of a category. And it's this. I suddenly start to care about reasons, and giving name to these reasons. And now that I have reasons, I can manipulate them. Like I have these arrows and I can compose them, and this is an operation, it will give me another arrow. They are mathematical things that I like to get my hands, I can get my hands on. While when I'm working in a proset, there's no such thing as, okay, give me the reason of why 3 is less than 5 out of all possible reasons, and the other reason that, and I will do something with them. There's no such thing. And this is very relevant to what we're doing here, because it's the same shift of Or like, it may feel like you're putting your glasses and you see more details. And it's the same shift that happens when you go from thinking like, when I'm proving a theorem, let's go back a bit to this idea that we had, where I have like my givens and my goal and all those things. And we had like, on our givens, we had a list of propositions, like I know A or B. Let's say my goal is to prove A and B. And I'm starting to say, okay, so essentially I'm here, A or B proves, I want to prove this thing, to write a proof of this thing. And now I have to say, okay, so I have a disjunction and I want to know how I can use it, or I have a conjunction on my goal, I want to know how to attack it, and all those things. We could write this proof, like to remember how it works. But the important thing is that somewhere down, like during your ideas of the proof, eventually you may have something like x, which is an integer. And there is this very bad feeling here, if you are kind of hygienic about these things. In the same table, you have like mathematical objects and propositions. And this is weird. So one way to get away from this is like you say, okay, I don't care, it never bothered me, it never will, and okay, you can step out of this class altogether. But like the other thing you can do is like, okay, let's start treating like, how should I, let's call it an H. I'm thinking of the word hypothesis, or maybe, I don't know, a D, maybe I'm thinking of the disjunction, or an S, maybe I think of summation. In any case, instead of giving labels like that, let's say that I have an object which is a proof of this disjunction, and now this becomes like relevant. This is the idea of proof relevance. So the moment you do that, you do not say, from this proposition I want to prove that. You will say, okay, I have something which is an evidence for that, and I'm required to produce something which is an evidence of that. And all mathematical proving becomes, let's construct terms of certain types, because the idea is that, as we have started seeing, that proofs and types, like types can serve as, I said proofs and types, that's wrong, propositions types. Like types can serve to encode propositions. So the object of proving a conjunction becomes the object of finding a certain term that inhabits this type. Okay, have I lost you completely? Like the idea is that suddenly I want to care about the reasons, and it might be different to say I have this proof of A or B, and I have this proof, I have another proof, of A or B, and this may be very different. Maybe S managed to prove this disjunction by selecting left and managing to prove A, and maybe T managed to prove this disjunction by selecting right and proving that B holds. So these two things are very different, but I have them both and I can use them in order to construct my goal. Are we, my point is the following. The same shift of perception that happens here, or of way of looking things, yes, is the same one that was happening here when you go from prosets to categories. You say, now I want to care about the reasons, I want to have them as objects, I can use them, compose them, blah, blah, blah. I don't care just about the fact that this is true, I want to know why it's true, what's the construction that shows that this is true, and now these constructions are mathematical objects, and I compose them, I can apply this one, it's a construction of a function, which, of an implication, which means a function, which means I can apply it to a construction of its domain, and I will get a construction of its something in its codomain, and of its codomain, so like questions right now, it's a good, this kind of question is good if we discuss them here. In Zulip it may take lots of pages, but that's not a problem, but just saying. Are we okay with this? Yes? What thing? This one? Okay, bad example. Swap this. I mean, it's not really a bad example because I'm talking in a like. No, sorry. Can I do that? Is that okay now? My point is like, select some random, okay? But very good point. This one I can prove, right? But okay, actually, okay, actually it's a good example. If, okay, you are right, I cannot prove this, but if I give you some further stuff, you can prove that. Okay, what I'm saying sounds trivial because if I give you this, also you will be able to prove it, obviously, but I don't want to say something as trivial as that. Okay, let's try to make this connection here. And I will also give you that from A, I will write implication like that, pardon me, you get C, and from A you get D, and from B you get C, and from B you get D. Okay, let's say you have all those things. Do you think I can prove it now, maybe? Maybe it's not so obvious. Okay, so like you have A or B, you have a way that from going, I'm trying to advertise here a different way of seeing this. You have a way from going from A to C. Let's draw these things. That's my point. Normally it's not how you would prove this, right? But, okay, how would you prove this? Let's see. You have implications here, which means you can transform A's blah blah, okay? And you have a disjunction, which means you can split in cases, and you also have a conjunction, so you have like a choice here. All these things, I hope you agree with me, are useless at the moment. Because all these things are implications, and implication, in order to get advantage of them, you need to have their input here, and I don't have A, and I don't have B. Because I don't have A, these things, since I don't have A, these things are useless. Since I don't have B, these things are useless. So my only hope is to look here or here. RT, pick one. So you look here, right? Okay. So you say something like separate by cases. Using this thing. And now, what happens is, this is very dirty. Okay, I'll write it here. You had A or B. You had A implies C. You had A implies D. Had B implies C, and B implies D. And you want to prove A and D, A and B. What am I even doing here? I'm confusing my letters and nobody's complaining. I don't know if I should complain about that too. You should too. I meant to have CD here, and I meant to have CD here, obviously. Otherwise, the other things are completely out of nowhere. C and D. Sorry about that. Okay. So essentially, I will either use this or attack this. RT said I will use this. Separating cases you're using this thing. But if you decorate them, like this is my disjunction, and this is lack of better names, or actually I will give some weird names, and maybe you will remember why I'm giving these names. So from A to C, I will call this U, and from A to D, I will call this V, and maybe someone's starting to remember something out of these names. If you were here, and I will call this I, and I will call this J. And this one, okay, I'll call it an S to remind me of a sum. Okay, so I will not say that I'm using disjunction, I will say that like I'm using S here. And it means that now, what are the two cases? The left one, which is the left case? I need to say that like from A and all those things, I need to prove C and D. And let's say I proved I have to prove this, right? And then there's the right case that I need to consider, which is like from B and all those things, you need to prove C and D. And now you say what? What's the next thing you can do here? I need to prove both things. Yes? Okay, so Maya here is like in let's use mode. Yeah, and you can do that. Or, I mean, it's fine if you do that at this point, but it's like, let's wait a bit for that. Okay, there are two things you can use, right? You could use this to obtain a C and this to obtain a D. Very well. Another thing you can do is like saying, okay, I will attack the disjunction here, so I will split my proof into parts, the left part and the right part, and then you realize you need more space. Okay, let's say like that, part left. What is the left part? It's exactly like this was, but I need to prove C, and I need to prove this, obviously. And here I will do stuff like Maya suggested, and there's a part right. Sorry. Where the idea is that out of these things, I need to prove D. And you understand what the skeleton of this thing is, like the structure of this proof is. I will have something similar here. I think I have space to do it in one page. Like this thing will get copy-pasted. But here, I do not have A, I will have B. Are you guys following, or is that okay? And so now I have reduced all the creativity that I need to like I need to prove these things, right? These four things that I need to prove. And I will do what Maya suggests, I will prove it. Does this remind anything to any of you? Especially to those that were like here in the last lecture? Or who have seen it, or... just a second, Proper Sotiris has a good insight, but before you say it, someone could say it definitely should not remind me anything because we didn't do a single proof like that in the last lecture. But the whole concept, the whole like moral story of this course I'm teaching is like things that look different are essentially the same thing. This triangle, remember, like we're talking about. Sotiri, what does this remind you of?
I was thinking to do the cross product and start putting all the objects and pointing the arrows there.
Okay, so very well. So like in the last lecture, we did something that looked like, that. The idea was, and actually we did it twice, so let me focus on the first one. We had a sum and a product, nothing to do with proofs, right, and propositions. It's a category, and there is a sum in a category and a product in a category, and we want to see how we can get help in order to find an arrow here. If I translate this to my world of propositions and proofs, it's like this is a proposition, A or B, this is a conjunction, C and D, and my objective is to prove it. What does it mean to prove it? Find an arrow from this to that, right? I want to prove this, and for each arrow that I'll find corresponds a proof. Each proof in this world is an arrow. And now I can ask help, like Arete did. Where did you start, really? Did you ask for help? Let's try to think. Did you ask for help from the fact that you are leaving a sum, or from the fact that you are entering a product? I know. So Arete is complaining, I was not in this, but you were here like 3 minutes ago, and you did exactly this without realizing it. That's my point. Because you had a disjunction on your givens, which means the left-hand side of the arrow, and you want to prove a conjunction on the right-hand side, and you had a choice. Do I split my goal? Like, do I ask this guy for help, or do I ask this guy for help? And you said, let's separate cases. So you said, I'll take advantage of the fact that I'm leaving a sum, and this will reduce the thing to two new goals, which were this. Prove from A, in case you are here, find an arrow that goes there, and in case you are here, find an arrow that goes there. And then, how do we solve this? And let's say, okay, in order to solve this, I will now ask for help from this thing. I will split the proof in two. It's a conjunction, and now it means that I need to prove this, and I need to prove that. And I'm done from this part of the proof, okay? Does that sound, do we start to see like the resemblance of what's going on here? Okay, and what would that be? This would be like, I don't know, Maya maybe started saying, let's go back to where I was writing these things. How would the other drawing look? Instead of separating by cases first and then doing this, you would say, okay, I will split my goal first. So it means now that I have a left part and a right part. And what are these two parts? The left part is, let's think about it. It's like with the same givens I had, prove C, and this is with the same givens I had, prove D. And how will I do that? Well, the first given I had here was like this disjunction. So now I will use the disjunction to separate in these cases. So what would be the first line in this part? Somebody? Yes? Yes. You said again, but you were looking here, right? Because it's the first time you're using, yes, okay. So this is separate in cases. You are using this thing. Separate in cases, and then you will have a left case and a right case. Sorry. And you will have to prove this too. And similarly, okay, so what is the left case here? It's like A. The disjunction A or B becomes A, and you need to prove C, and here it becomes B, and you need to prove C, and the whole thing now, I hope I will not mess it up, will be like that here, but here you need to prove D and D. Like, you apply this in your class of teaching initially proofs and logic and stuff, and one student solves it like that, and one student solves it like that. And obviously you're in a university because you don't see this in high school, right? And then you can ask something like, are these proofs the same? Is one better than the other? Are the proofs equal? Okay, so if you see proofs as constructions, you get the right to compare in a objective way proofs, to have an equality between these arrows that you have. And you're obviously, as I said, in a university kind of setting because you are doing logic and this is very advanced. And then you remember that when you were in, I always mess this up, elementary school or high school, I don't know. I think this is elementary school. I want to hope that it is. And you say, wait a minute, like, at some point, my teacher back in school asked us to calculate, let's say, not say proof, like, it's the same thing, compute and proving, something like that. What do I have here? I have this. I will even use like Greek letters in order to pretend that I'm in Greek elementary school. Like, calculate this. This is equal to what? Because you are, is this indeed elementary school or not? Or is it higher? It is. Last year of elementary school, maybe. Come on, it's maybe not with letters, okay? Yes, letters are scary. Maybe you did that like with numbers. Okay, but the first year of high school, you get to introduce the idea of variables, and then you did it with letters. So, and like, what would you do here? You know, you studied supposedly some properties of multiplication and of exponentiation, all that stuff. And okay, so you say, it's a product. Product. And it's an exponent. And you get to mentally, you have too many things to apply, and you have to make a choice. Will I see this as something that is being exponentiated to a sum, or will I see this as something that is being the exponent of a product? Okay, so here you would, one student would do something like that. Sorry, okay, this student didn't really study, he's trying to cheat. But okay, you would do something like that. And then what would you do? You say, okay, this is actually gamma to the power of alpha, gamma to the power of beta, this is delta to the power of alpha, and delta to the power of beta. Okay? And the other student would take a different route here. Would say, aha, this is something that is being elevated to the power of a sum. I know what I can use. This is gamma delta, this thing to the power of alpha times gamma delta to the power of beta, right? And what did they do next? They did, aha, this is gamma to the power of alpha. Now they remembered that they know the other thing as well. So this is something like gamma to the power of beta and gamma to the, delta to the power of beta. And maybe you wonder about the same thing, I don't know, like whose proof is better, whose calculation is better here. And it's essentially the same thing that's happening. Like this thing is this thing, which is, I will not scroll back to this page I had, which is the left or the right, I don't remember where I had which is which, and this is pretty much this, and it's pretty much the other thing, okay? So we should have to understand a bit better all this idea between computing, calculating things, proving things, and also using tools, like more abstract tools from maybe algebra category here and stuff like that to understand what's going on. Like questions. So does this make sense? Like the thing we did in the last thing is something you did again here, and something that you would have done if somebody gave you like this simple logic exercise. Maybe I have this specific one, I don't remember, in this homework to solve, like, let's try to learn how to use this language of proofs to do stuff. Questions? No, okay. So, back to this thing. We also saw a bunch of categories, usually called concrete, where the objects look like sets with extra stuff. And in these things, usually the arrows are the functions of the underlying sets that respect the extra stuff. So like if you have groups, the arrows will be the group homomorphisms, functions from the carrier set of the group to the carrier set of the other group, such that they respect all there is to respect in a group, which are three things: binary operation, unary operation, nullary operation, so like multiplication, identity, or unit element, or a neutral element, how you want to call it, and inverses. And similarly for all the other things we have met. And the second family of categories that is really interesting because it gives a way that you can see category as a generalization of a different thing, not of a proset, is the one that comes from a monoid, because you realize that if I give you any monoid, you can look at it as a category where these little sets that I put here are all the members of the monoid, and this is just a bullet. This was like the first example that we saw of maybe a category with many arrows and a few objects. And in this way, it's like saying, okay, if you have a monoid, your world looks like that. But if I have a category, I may have other objects and I may have other arrows. So like if you give me, so in this sense, a monoid is like a special kind of category, one that has only one object. Okay, does that make sense? So you say, okay, let's not have this restriction. Let's study a world where we can have many objects and arrows between them and all these things. Okay, we've seen some more constructions that I don't want to mention right now, but the essential thing that happened in the last lecture was that we started giving categorical definitions, which are definitions that make sense in any category, and it's fun and quite illuminating to see how they incarnate in different categories. The same definition, like we defined a product, and we saw that product, I should have some examples here that we wrote. Okay, first we define what is a terminal object. Okay, it's an object in a category that guarantees that from any object you like, there is a unique arrow that gets into this so-called terminal object. And now we have a way to say, okay, let's look who are the terminal objects, if there are any, in all the categories we know so far. And you were supposed to do a lot of that, and I think this got pretty much ignored, most of it. But you can imagine, like, you have an ever-growing table of fun exercises where you have, I don't know, like the notions you learn, the categorical notions, you say, aha, terminal objects. And then, and remember, every notion comes with its dual notion. So if this will be the columns here. So if your matrix, the table you're writing, if it has an odd number of columns, you have something weird. Maybe you learn products, and we also see in co-products we will call the sums. And I don't remember if we saw something else, but like I already have 4 columns, and what is like the rows, it's one for each category. Like you can start with these categories, maybe ask yourself about, in general, n, then you start like considering the, okay, let's go to the integers with divisibility, maybe the integers with this. Then you say, okay, these are just all posets. Maybe I can figure what's going on in a poset, and then you go like, maybe I can figure what's going on in some monoid, or these categories that I mentioned, like category of sets, monoids, I don't know, groups, rings, posets. Be careful, or prosets. Be careful. This is not this. Okay, this is the category of all prosets. What are the arrows there? Somebody please help me. The word is my word of prosets. So I have a proset, a proset, a proset, a proset, a proset. What are the arrows that get me from one to the other? Yes? No, the suggestion was like injective functions. They don't need to be injective, because like in a proset, that's not what is important. In a proset, the important thing is, wait, in a proset what matters is the relation you have, the order. So like, as I said, these end up being functions that need to respect what's important. So what is important in this would be, what Areti said, if the important thing was distinctions. Injunctions are things that respect distinctions. In a proset, the important thing is the relation we have, the order. Yes, Lazarus?
Functions that respect the order, maintain.
Yes, that preserve, as we say, or maintain, maybe, yes, which are called like monotone or isotone functions. Okay. So this is it's the category of prosets. Its objects are prosets and blah blah. This is not one category. For your favorite poset, you plug it here and you look at it as a category, it's a completely different thing. You can understand that between 2 prosets you may have a bunch of arrows. So this category in particular is not a prosetal one. It's not thin. It doesn't look like any of these categories here. Is that okay? Okay, and now what is the object like of this form? It's very illustrative, and you should do a similar table when you start learning topology, because topology also offers you a rich language, and you say, aha, now I know what compactness means, and now I know what it means to be connected. And what you should do every time you learn a new topological definition, it's a good idea to say, give me all the topological examples, the good examples at least, my favorite ones, examples of topological spaces, and let's see for each one if is this space compact. I just learned what compactness means. So I want to test which of my topological spaces are compact and which they are, and eventually I realize and understand better what compactness means. And I understand better this topological world, right? Okay, now we're doing categories, but it's exactly the same idea, because both offer a rich language and similar ways of investigating these ideas. So Before the break, I want to remind you what are, to remind you what are the categorical definitions we have seen, and I think it's only these four. Anybody remembers if we have seen any other one? I think not. And we should investigate. I should not do this for you. I maybe do a couple of these things, but like we should start investigating this. And actually, I remember right now we have seen other categorical definitions that characterize special arrows and say, aha, let's give a name to these arrows that behave like that. They are quite cool. And the arrows that we have, the names we have given to arrows to single out some cool arrows were these. So we know when to call an arrow a mono and what it means to be a monomorphism, the real definition, let's say, the correct one. What's a split mono, what's an epi, and what's a split epi. And what's an iso? Where is that? I know we have seen isos as well, it's somewhere. So we have like products, coproducts, terminals, and initial things. We know what these things mean. And for any arrow, I get to ask at least 5 questions about this arrow. Is it a mono? Is it a split mono? Is it an epi? Is it a split epi? Is it an iso? Okay, so it's a good practice to start. As soon as you see an arrow, okay, I know 5 things, 5 adjectives, which apply to this one. Okay, let's stop here for a break. This review goes way longer than I expected. Let's come back in like 11 minutes for mysterious reasons. Okay, so let's start testing those things we have, the things we know. And okay, I'll quiz you like quickly in some categories. Like let's go in the category set. And the question is, do I have a terminal object? Do I have an initial object? What about products? Terminal object or initial object are like, they are either there or they are not, and they could be one or more. And it was an exercise to show that they are unique in a categorical sense. And actually, I want to start from this thing. So spoiler alert, I will do a homework for you, which I don't tend to do. But like, let's see what uniqueness of terminal objects means. And we'll see that it's usually, I think most of you are familiar with the term unique up to isomorphism, but we'll see that these kind of things are even more unique than that. It's what we say, it's unique up to unique isomorphisms. So it doesn't really mean that any two things that satisfy this are isomorphic, but they are isomorphic in only one way. There's no way that you can find an isomorphism between them and I find a different isomorphism between them. They're even more unique than that. Okay, so first I need to understand what I'm trying to prove. It means that I'm in a category, let's call it C. What does uniqueness mean? It means that I have objects T and T prime, and they both deserve the name terminal objects. And my objective is to prove that they are isomorphic. Remember, isomorphic means that I can find an iso from one to the other, and remember this means it's an invertible arrow. Okay, so how do I do that? Like almost every proof in a category, I need to start drawing things. And the more I draw, the less I write. This is good. And the better vision I have in order to understand what is going on. So T is a terminal object. What does that mean? It means that for any object X, there is a unique arrow that goes from X to T. Okay? And T has the same property. T prime. It's also terminal. I want an idea. Some students are missing, so it's more tense for the rest. So I need an idea of how I can do that. So this is what I want to, okay. So what I want to satisfy my goal, okay, if I look at that goal, I see it's a lot of things, because it's not just that I need an arrow, but I definitely do need an arrow, but I need an arrow that's an ISO. So I need to find an arrow, and then I need to say why this arrow is invertible, and even then I'm not done. It sounds like too many things I need to do, because it has to be unique. Remember, I'm sorry, forget what I said. No, nothing like that. It just needs to be invertible. So in order to justify that it's an ISO, it means I need to find its inverse, some arrow going this way, and check that indeed this composition is the identity here, and this composition is the identity here. Okay? So ideas of how I can do that. I can keep saying that, but actually, I hope that you realize that this is very wishful thinking. I don't have, this is what I want. So actually, I don't have the right to just draw an arrow and say, aha, this is which arrow. My world for the time being is like that. And even the blue things here are like quantified things. For any object you like, you get this. For any object like this, essentially, the only objects that I'm looking at this point in my category, which I don't know which it is, but I have called it like C, has these two guys here. Okay, it has a T and a T prime. And I know that they have this universal property. Okay, I know that any object I pick, I can ask for this thing, since it's terminal, I can tell it, any object I pick, give me the unique arrow here. Same goes for the other one. Yes, Lazarus?
If T is terminal, then we have an arrow from T prime to T.
Very nice. So you say, I will take advantage for the fact that this is a terminal and just treat this as an everyday object. In fact, it's for any x, so this x can very much be this T prime. So you get an arrow, a unique arrow, actually, just by the fact that T is terminal and T prime is just an object. Okay. But now, okay, so you say, aha, at least I have an arrow, and now I have good chances of managing to prove that it's an ISO. So how do we do that? What do you need to prove? How do we finish this proof? You need to tell me of a different arrow that goes this way, and I say, wow, where can I find arrows that get inside T prime?
The same way.
Yeah, T prime is a terminal object, and T is an object. So there is a unique thing that goes this way. Are we done?
We have to show the composition with the identity.
Both compositions. And you say that, but it is, yes?
This is mandated by the identity law. Because we have also...
The identity, no, wait. Okay. Be careful there. The identity law guarantees that there is at least a specific thing like that, and that it behaves, let's call it 1t, and there is such a thing like that here, 1t prime. And the identity law, first of all, the fact that it's a category guarantees that these things exist and tells you which they are. And the law tells you that if you compose with them, they do nothing, right? They are identities. But what you want to prove is that this composition here is this one. And you don't get that from the fact, from the identity law. It could very well be that this composition is some other thing here. And you would not have the right to say, aha, this is an ISO, because you haven't proved that this is the inverse of that. Maybe this has nothing to do with that. Like, think of the successor, think of that, like this is the natural numbers. Okay, they are not terminal objects, but think the natural numbers. This is the successor and this is the successor as well. The fact that you get successor, that's not that's not the identity function, right? And since I gave you an example like where this does not happen, it probably means that you should again use the fact that these are terminal objects somehow. And so far, you have taken many things that you have not used, like you know that they are unique. And if you look at it like that for a lot of time, maybe you'll figure it out, maybe not. But sometimes it helps to open up the diagram and duplicate some things. And this is what I'm going to do now, because I'm going to duplicate one of them. It doesn't matter which one you choose first, you'll get the idea. So I do have a unique arrow that goes from T to T prime, and I will duplicate this T in a different place. And I do have a unique arrow that goes from here to there. Lazarus has justified both of these arrows. This one, because this is terminal, and this one, because this is terminal. What I want to do in order to justify one of the two things that I want to justify is that the composition of this and that is what?
Identity.
Yes, exactly. Thank you, Panos. So I do have this thing, right? So what I need to verify is that this commutes. What does it mean to commute? That the bang times the bang is equal to 1. Okay? Where do I get that from? It could very well be that this, composed with this, is not the identity, it's some other weird arrow from T to itself. Yes?
The fact that T is terminal doesn't get...
Now it's kind of funny, because I'm going to ask you which T. Because as far as I have this diagram, I mean it's the same T, okay? But in order to understand the picture, which two are you looking at? The top one or the bottom one?
I'm not talking about the
Oh.
particular T.
Only to identity the uniquely, the terminal.
No, wait. The identity, the uniqueness of the identity, it just means that only one arrow here deserves the name identity.
But if there was a second arrow,
Yes?
then it wouldn't be terminal.
Okay, so you are looking at this T, and you're saying, look, this T is terminal, which means that there is only one arrow getting here from any object, in particular from itself as well. Does that make sense? So now I know that from T to T, there's only one arrow, and I know that the composition goes from T to T, so it can only be this arrow. Does that make sense? Okay, so I hope it was not like too difficult. Maybe the first time you see it, you are really wondering what is it that you need to prove, and this is like why I'm kind of holding your hand with this a bit. And now, like a homework that has been assigned, it's been a long time, there's like a second question is like, what is the best way, am I done? Technique, yes?
You have to do the same for T prime.
Yeah, so I need to check that the other composition, like this one, yes, so this one also commutes, okay? And for the same reason, commute, so we finish this proof and we are done. Another question is, what about initial objects? Are they unique? Yeah, you get it from the duality principle, but I want to analyze why this holds. What does it mean? Like I am in a category C, I do have like I and I prime that are initial objects. I will call them coterminal here to emphasize my point. Coterminal, it's the same thing. And I want to prove that they are isomorphic. And I could do a similar thing and say, it's similar to the thing above. I want to do something better. Because this similar, you cannot really get it automatically. You get it because you count on the mental capacity of your colleague that they can do a similar thing, right? But I want to get it in an even better way. I want to directly get it for free. And I say, okay, wait a minute. So I have a category C, and in it, E and I are coterminal. This means, remember this construction, which is the opposite category. So if I look in the opposite category, I do have that I and I prime are terminal there, because it's a dual notion. And I already proved the uniqueness of terminals, so I know that they are isomorphic there. But isomorphic is, as we say, self-dual, it's the same thing. So for free, I get it in my initial category. Essentially, I have any theorem that I prove that has this form for any C, which is a category, something blah 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 holds, any theorem like that, you can get this, dualize it. What does that mean? You change all sources for targets and all targets for sources, and you change all compositions like that to compositions like that, and that's pretty much all you do. So pretty much any diagram that appears there just gets all its arrows flipped, and you have the dual version of this theorem proved for free, because since you have proven it for any category, a particular category will be this one, and in it, this is the statement that the dual of this statement is exactly this that you were trying to prove. So, like this was a homework to kind of think about it. It's not like do a copy paste and fix things. It's just apply to the duality principle and you get any theorem for free. The only times that you will feel like you were cheated because they promised you promotion like 2 theorems for 1 is if it happens that the thing you prove is self-dual. So the dual of it is itself. So you say, okay, where's the promotion? Okay. But in any other case, like this one, which was not self-dual, we prove that terminal objects are unique. This does not mean that in any category you have a terminal, say, aha, I will apply to the principle of duality, and I also get an initial. No, because we never proved that any category has terminal objects. If we prove, and we will not because it's not the case, if we had proven that in any category there is a terminal object, we would also gain for free that in any category has an initial object, but it's not the case. Okay, so you found a terminal object, okay, that doesn't mean that you get something like that for free. But you prove a property of a terminal object in an arbitrary category, you get like uniqueness of like exactly what happened here. We proven uniqueness of terminal objects, we get uniqueness of initial objects as well. Are you with me? Okay, yes, Lados.
Don't we have to show that the operation of taking the opposite category respects such relations?
Actually, I think I didn't even, I was thinking that maybe I didn't even actually define this properly, and I kind of said it orally. So you want to respect the word I'm missing here. You want to say that this operator here is good in some way, right? The argument goes here. So this dualizer of categories is a good thing. Behaves well. Okay. So this is the notion I'm missing, and I hope we will get to this in this lecture, which is the notion of how I get from a category to a category. Because essentially, this thing takes a category and goes to a different to another category, let's say. So like we will figure out how to express your worry in a few minutes. And then you say, okay, I want to prove that products are unique in the same way. And how would you do that? I will not do the whole thing. I will do the bad way of doing it. You will say, okay, what does it mean? It means that I have like A and B, and I have 2 candidates for a product, P. Remember, a product is not just an object, it's an object together with specific arrows that get into A and into B. The whole blue thing, let's say, is a product. It has its own, I don't know, out left and out right. And I have another one, let's make it orange. Let's call it P prime. And it has its own way of getting here and getting here. Okay, and I want to prove that uniqueness of products. What does that mean? Categorially means that if you have 2, they are isomorphic. Any ideas how I can do that? So I do have P and P prime is I'm using A, right? Is a product of A and B. I'm in a category C, and I want to prove that these things are isomorphic, but it's kind of a question like, okay, what exactly does it mean to be isomorphic? Because I just said that it's not just the P's, right? It's this whole blue thing. Essentially, I want to say that the blue thing is in some way isomorphic to the orange thing, okay? This means that I need to be able to find a way to go. I should pick a different color. I don't know, like that. I need to find an arrow like that. Where do I get an arrow like that? What happened I used so far? Okay, pretty much anything, but like that they are products, okay? Remember, the characteristic thing of a product is, first of all, it's a whole thing that has ways of getting into A and getting into B, and this as well. But like, one of the two facts, either this, the fact that this is a product, or the fact that this is a product, is going to help me to construct an arrow like that. Which of the, do I ask for help from the blue thing or from the orange thing? So the product was defined in a way saying that any other candidate, there is a unique way to get inside your guy. So it means that the fact that this is a product gives me a way to get in for this arrow out of any other candidate for a product. So I will say, I will take advantage of the fact that it's a product and ask for this thing to give me the unique arrow that makes these things commute. So I get this arrow. And just like before, I would like to show that it's an isomorphism, which means I need an arrow the other way around. And now I do the same thing, because if I start drawing like that, I will lose it, okay? So I duplicate this P here, together with all its arrows, and I'll say, okay, thanks to the fact that this is a product, there is a unique thing that makes this commute, that goes from P to that. Now, thanks to the fact that P is a product, but I will not look at this P, I will look at this P, I also get away a unique thing that makes this thing commute. Does that make sense? Okay. Am I done? I'm in the same stage I was like in the previous exercise. I want to guarantee that this composition is unique, that makes these things commute. And if I spell out everything that I need to spell out, I will get this as well, and I will not be done yet. I will have like also to check this thing. I don't want to do the details here. It's not very time consuming. You should be kind of convinced that this will not be very difficult to do. It's kind of more interesting here because I have all these commutativity properties to use and to worry about, which was not in the case in the terminal object. And there's again this question like, what is the best way to prove this? I tend to ask these questions because, okay, so right now if we pretend we have proven this, completed this proof, and I ask you, what about coproducts or like sums? You will probably say, okay, if you were not paying attention like 5 minutes ago, you will say, it's similar. You will just end up doing things in the other way around, and your argument probably will work. So it's proof by similarity, okay? But you're kind of cheating. But if you were paying attention 5 minutes ago, you would say, I get it for free because co-products are just products in the opposite category. So, I got it for free, and I will say, maybe I can do even better than that. And in order to do even better than that, you need somehow to say, this looks an awful lot like what happened in initial and terminal objects. Maybe I can get the first theorem approved here, which was uniqueness of products, as a special case of uniqueness of either initial or terminal objects. And if you remember the definition of a product, let's say if you look at the fact that this guy here is a product, It means that out of any other candidate, there is a unique way you get inside this guy. And now comes the point that you start appreciating abstract stuff, or maybe it's like a cultural shock or something, that you say, okay, let's see if I can make a category whose objects are candidates for products. So whose objects are these elastic things. So like, let's see if I can make a category. I'm trying to find the tool here that highlights stuff, and I'm not finding it. Okay, I found it. Let's try to see if I can define a category whose objects are these kind of things. Like here's an object of this category, here's an object of this category. Here's another object of this category, another object of this category. Do you see what I mean? Like, if I make these as an object in a category, and I define what arrows means in the category in a good sense, I will not even have to prove the uniqueness of products, because I say, products are just terminal objects in this new category, and I know that categories have unique terminal objects, so I don't even have to do this work here in order to get co-products for free. I will get both of them for free if I manage to express all these things as objects in a category, and these things as the notion of arrows. And if you see this, maybe you have a good idea of what an arrow should be in this new category. Like, if your objects are things like these, what would be an arrow that gets from this thing to that thing? Do I have a suggestion? So I'm trying to say here, like, I'm defining a new category, and the objects of this category are things like that look like that. These are called spans over. I mean, I'm fixing A and B in some category, and I'm now want to define a new category, and the things will be like the objects will be things like this thing, all this thing I have drawn here. So here's an object, the gray object. Here's another object, the blue object. I don't know, Q. Here's another object. So and this also come with, like, okay, let's call this like P1, P2, and this may be Q1, Q2. And this is like R1, R2. So the blue things, sorry, I should forget what I said, the blue things. My idea was to make colorful the objects there. So, okay, let's do it. I will make this dull, and I will colorize like what's missing here, like red, okay. Okay, so bear with me. The colorful things are the object of this category. So what is an object in category? Some object in the original category, together with two arrows, one that goes in specifically into A and one that goes specifically into B. Sorry, this should have been gray. Okay, and now my question is, what is an arrow from yellow to blue? Or what is an arrow from red to yellow? Anybody wants to give a shot? I do have like an original category C. I will make it gray. But like this new category that I'm defining, maybe I could call it something like that. We'll see a better way to do that later on. But so out of this kind of shapes, I want to get a category, right? So I told you what the objects are, ideas for the arrows. What should count as a way of getting from the red thing to the yellow thing? Ideas? I do have an original category, I can ask for things there.
Arrows from P to Q, from the objects of
Okay, let's be specific. From the red to the yellow, okay, would be an arrow from where to where?
Από το P στο R θα κάνουμε.
Okay, very nice. So an arrow from P to R. That's like So if my original category doesn't have an arrow from P to R, I will say in this category, the new one I'm constructing, there is definitely not an arrow from the red to the yellow. Am I done? Is that enough? Remember what happened in the products?
Πρέπει να κάνεις θυμάται άρρος στο τεχνικό. Το οποίο είναι στο αρένα.
It's not a way of mapping them. It's a way that your arrow should take into account the rest of the picture. I mean, your arrow should in some way. It's not. I mean, you are expressing the correct idea, but it's not like mapping the arrows. Somehow you need to take off account of the whole thing to transform this into this thing. And if you only care about this thing, that's not a good idea. You are forgetting that you worry about this thing becoming this thing, and not just about this thing becoming this thing. And the thing that's missing here is that your arrows should be an arrow from P to R that makes this thing commute. So I have just defined a new construction for categories. Should make, okay, so it's like, what are arrows in this new category? They are arrows from the point, from this point to that point in the original category, such that in the original category, they behave well. They make this thing commute. So they take into account this thing and that thing. Okay? And this is also why you really need, like in a product, to not say just P is a product, it's P with these things. Because maybe for the same object P, I have chosen a different kind of arrows, right? So now there's a different thing that needs, different triangles that need to commute if I make this different choice. Okay, I have described, maybe it seems a bit silly, like, but if I verify that this is indeed an arrow, sorry, a category, I don't get that for free. What do I need to worry about? There are few things, like, I need to say, does any object every object has an identity? What are objects? Things like that. Okay, so why does this thing have an identity? I have to worry, okay, what is an identity here? It means that I have like this red thing here that goes from A and B, and I have itself as well. And I'm wondering if there is an arrow here that behaves the way it behaves. First of all, why is there an arrow from here to here? Yes? The identity. So if I ask, okay, first of all, why is an arrow in the original category, why is an arrow from P to P? Because identity guarantees that. There is this arrow here, the identity P. Why is this an arrow in my new category? Because remember, it's not just any arrow, it needs to have these things need to commute in the original category. And they do thanks to the identity laws in the original category. So indeed, I do have an arrow from P to P, but I don't yet get to say that it satisfies the identity law. I need to test it. And when you test it, and you check that it does. So, and the same thing about the associativity law. So in general, we have a new construction for a category, which is like this one. Like for any, pick your favorite category, select two objects, and I get a new category, which is of all those spans here, roofs over A and B, and I consider these the objects and not the arrows. And I get a lot of things for free like that. I mean, I say, aha, you were wasting, okay. You were doing like the professor of the course asked you to do, to exercise these things, and you solve this in this way, and now you find out, aha, there's a much better way, because tons of these things that we define in category tend out to be special cases of initial and terminal objects. You just shift the idea of in what category they end up being initial and terminal objects. So a product between two objects in a category is an initial object in this category that I get out of from the original one. And I have like 10 minutes here, and I promised I would get to this, and I don't want to we could see more constructions and more examples and like play a bit with mono and split mono and stuff like that. Yes,
Στο πλαίσιο των proof assistance, αυτό που δεν έχω πιάσει είναι πώς κολλάει το category theory. Δηλαδή, θυμάμαι το triangle που φυσικά είναι στην αρχή, αλλά το connection.
Okay, you said proof assistance. I want to see it like a tool. I mean, you see it like maybe in programming. So like,
Ο στόχος του μαθήματος, ένας στόχος του μαθήματος είναι και η proof assistance. Οπότε αυτό που καταλαβαίνω είναι το category theory πώς μπαίνει σε αυτό το...
Okay. As a kind of a hint of an answer to that, maybe not very satisfactory at this point, but remember what we did like in this class today, in the beginning, I didn't actually open like Lean or Agda to write code, but these like commands that I wrote there, like split, blah, 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 and all this stuff, you could see it, you could consider it like a human proof assistant. So like, and like in the previous class, we were doing like category theory, trying to figure out how to get an arrow from there to there. And pretty much we saw two diagrams. Where was that? Just give me a second, I'll find it, I think. This thing, like, these two things. So like this, you say, we are doing category theory, this has nothing to do with proof assistance. We have translated this into two different programs, right, that are proofs in a proof assistant. And we understand kind of a bit better what it means to, give me, maybe actually, one thing that's missing, and I realize it now, that's important, is like, I haven't told you why there is a category of, yes, thank you, okay. So this is missing. I actually hinted at that when I said, alpha plus beta, arrow, gamma cross delta. But I think, I never mentioned which category I'm thinking here. So, okay, let's do that. Pick your favorite. I could do either proposition and types here, or I could say prove your favorite programming language as far as it's a good one, and this means like it has types. Yes. You have something like logic. You have like, let's say algebra. You have category theory here. You have proof theory here, and you have like programming. I will put type theory here. Programming notions here. Let's say, yeah. No. Okay. So like the short answer is you could like start doing only proofs or only programming things or only doing categories. You will be missing out, like, you will not understand well the things you are manipulating. I mean, okay, for example, you take a proof theory course and you understood what it means elimination and introduction of, let's say, conjunction. Okay, what is the introduction of conjunction? You have A and B, like if these are true, then A and B is true. It's fine. I get someone to blame for the thing. It's fine. So this is like, and you can say, I don't care about categories, I don't care about programming, I want to understand the logic. And I'm impressed by Genzen, who came up with the introduction elimination rules. So what are the elimination rules? There are two of them. Out of this you can get A, and out of this you can get B. These are the elimination rules for a conjunction. I mean, you could say, okay, that's all I want to do. It would be fine. But then you realize that like a programmer is using this construction that out of an A of type A and a B of type B, he gets to program in his favorite programming language this thing. construction of forming pairs, and you say, okay, that's kind of coincidence, maybe. And then you say that, okay, wait, actually your favorite programming language, if I have something of this type, I get to project out of it. I get to get like first of W, which is of type A, and I get another projection there, right? And you say, okay, so actually what this guy is doing there, introduction looks like this, elimination looks like that, and Gedzen has like the inversion principle pretty much tells you that if you form something and then take it apart, you get up where you started, and this is exactly what the programmer says. Like if you do, like pretty much I'm hinting at the Vita and the Eta rules. Okay, and now to bring category here, because maybe you were already fine with the other two things. You say, okay, wait a minute, what is happening here? This is just a product. The introduction rule here is just saying that I have ways of getting inside A cross B. So these are like the things I have in order to form A and B. No. I'm being, forget what I said. So okay, I will write the thing and I will explain it after I write the diagram. It's a better idea. So I have these things, out left, out right. Okay, what is a product? It's something with two ways of getting to A and B. What are these things that I have here that get from A to B? Essentially, I have that from A, B, I can prove A, and from A, B, I can prove B. So now start looking at these things as arrows in a category. And you may have different proofs. You may care about different proofs that get you from something to something, and then you are lucky that category allows you to have many arrows. So like an arrow from A to B will be one for each proof of the fact that from A you get to B. So now you realize, the elimination rules are just the fact that this has the right form to be a product. And what is the rest of the diagram I have here? It says that for any other candidate means this and that, I have a unique way to get here, such that this commutes. And you may wonder, you may say, it's more general here. I didn't have anything of this nonsense of commutativity. I couldn't even say these things while I was being a programmer, And I will say, actually no, because like what you have here, this is just Vita and Vita, and I will leave as a pending homework ever since to say where is Zeta, because let's translate this. What is this Vita and Vita here? It's like the out left of this thing is equal to that, right? So you have an out left of remember how we called this arrow, right? This was like, okay, let me write this. Let's call if I call this F and G, this arrow here was like called the pairing of F and G. And what does it mean that computes? It means that the out left of F of the pairing FG is equal to F. So this commutativity here is like the first Vita equation that we had. This commutativity here is the other law that I have, and the fact that this is unique, there's a unique thing that makes this commute, this will end up being like the eta, because what does that mean? If you have any other arrow like that here, let's call it, I don't know, C. Essentially, you want to say, okay, I don't have time to explain this well now. I will leave this as a homework, and I will come back to it. Like, figure out. Okay, I kind of gave you the answer about these equations and where they are here. Like, they are these commutativity triangles. What about uniqueness? You may ask if you like categories and you are learning about programming now, or if you like programming and are learning about categories, you may ask, where is the eta? That like I had there that out left of any w paired with out right of any w, I had that this is w. Where is that here? Maybe I have richer stuff here. You don't. There's a perfect correspondence between that and that. With the hint is with eta, like try to think about to figure it out. So, okay. The next class will be to say how to go from a category to another category, but this was very important. And actually, somebody who cares about orders will say, these introduction and elimination things, what are these things? These are just, this is just the meats of another thing. Like if you remember, if I write this thing instead of this thing, then what does it mean for P to be a meat of A and B? It means, first of all, that it's an upper bound. So I have this and I have that. Lower bound. Okay, so I have this. From P I can prove A. From P I can prove B. So far I know that's a lower bound, but meat is the best lower bound, okay? So it's the greatest lower bound. It means if I have any candidate that can also prove both of these things, then mine is better, right? And what does it mean mine is better? I have this, okay? So, like again, the same idea shows up like in order theory as the meats, and you say, okay, now I may start to understand better that the world of proposition and proofs that I'm proving is like, if I look at it as a process, it's something that guarantees meats, because for any A and any B, I can form this thing. So you may start to wonder if you know like some special process like I know you do, you may start to wonder, maybe it's a semi-lattice, maybe it's a lattice. Let's see, for any A, B, is it really guaranteed that there is such a thing that satisfies this? And you find, this is conjunction. So meats are satisfied, and joints are satisfied. They are these junctions. What about terminal object and initial object? Or, sorry, I've switched to category without even realizing it. What about top and bottom? Okay, that's the false and the falsum and the truthum. Yeah, I will not yes.
Οι άνθρωποι που δουλεύουν σε type theory γενικά έχουν στο μυαλό τους τις τρεις διαφορετικές.
I think I will make a very bold and a very opinionated statement. You cannot really get to say that you understand well any of these things without understanding how it manifests itself in the other two. But this is not like something I can prove, like this is my considered a person.
Αυτή είναι η τελευταία ερώτηση. Το τριγωνάκι είναι γενικά στα βιβλία σε type theory τα ακολουθάνε κι άλλοι ή μέσα από την πορεία σου?
No, this is like, it has been coined as a Trinitarianism. I do have a link in my page on the MCAT lab, and it manifests itself. I mean, the thing is, okay, it's kind of fancy, kind of catchy. You say the Holy Trinity of math or computation, logic, or whatever you want to call it. Depends on where you approach it. But you will see that sometimes it's actually there's a fourth thing. Like I'm kind of sneaking order theory. You may say it's a kind of special kind of category, so it's very close to category theory as well. And you will see many triangles that manifest themselves like that. So it's like a concept that anyone has and may abuse to fit it the convenient metaphor. But like these three things, I will I will highlight the link in Zulip as well. Like but if you Google for Trinitarianism, I always mess up this word when I try to pronounce it. Trinitarianism, is that right? Is it correct? I don't know. The Holy Trinity of thing. You see it in you see a bunch of instances of this thing. Now, this is very, very well known as a connection. So I think We have pretty much run out of time. I will kind of ask you very strongly, as strongly as I can, post solutions to the homework, because I really need, like this was half class, half me being a teaching assistant, trying to solve things. And I'm really willing to be a teaching assistant in Zulip, but let's spend the time in the lectures to advance, supposing that we have worked a bit offline. So the next time I will start the course with finally telling you how I can get from a category to a category. And from that point on, we get to see, I understand what category theory studies, okay? Because so far we only know the objects of category theory, which are categories. What are the arrows? This is the key word here. They are called functors. So the idea is, I might try to come up with your own definition of what a functor is. It's a category. A category should be some kind of mapping from here to there that respects what needs to be respected. Pretty much, you cannot make a mistake. Okay, but we'll just make it. We'll fix it. We'll define it, and we'll have a way to get from categories to categories. So, till next time.